thank all of you for living through the traffic today, or the tea. I know the tea was pretty bad earlier too, but I'm really very happy that you could all make it to tonight's talk. Thanks for being so tolerant of all the delays and emails. It's really been a busy week. Let's see, a blizzard a week ago, the Patriots pulling a Super Bowl win out of the air. Yeah, and then yesterday's snowstorm. And so right now the piles of snow are over my head, and my arms and back are sore. But it's still really pretty outside, and so I hope you can enjoy a little bit of the weather. So my name's Lena Morales, née Genevicius, and I'm class of '82, and I'm the current chair of the Boston Seminar Series Committee, and a past president of the MIT Club of Boston. The MIT Club of Boston is an independent, nonprofit, member-supported, volunteer-run organization for MIT alumni living in the Boston area. And yes, I'm not paid for any of this. Don't ask me why I do it. We support the social, networking, educational, and service opportunities in the Boston area for the MIT community. Just so you know, we have 3 more Boston Seminar Series lectures on schedule this year. At the beginning of March, Ali Azerbaijani will speak about voice analytics, and I hope to get the details on that ironed out by this weekend and post it as soon as possible. On April 1st, Deborah Douglas and Edmund Golaski will talk about the tradition of hacks at MIT. And for that one, I'm praying that we don't get another April Fool's Day blizzard, which we did in 1997, if some of you might remember that one. At the beginning of May, Michael McCreary will speak about the display technology used by e-ink. I'm hoping to find a location on the route to Route 128 corridor so that people who live in the burbs might have a chance to see one of these events. So if you guys have suggestions, I'd love to hear them. And I want to thank Microsoft and Convene for their support for this BSS lecture. And I want to thank Cheryl Jones, who is unable to attend tonight, Bob Miller, who's going to be videotaping tonight, and Helen Berry, who's at the registration desk, for all of their work in setting up tonight's event. So I'm pleased to introduce Sam Madden. He's a professor of electrical engineering, computer science in MIT's Computer Science and Artificial Intelligence Laboratory. His research interests include databases, distributed computing, and networking. His name may be familiar, since in addition to his teaching at MIT, Professor Madden has taught courses through MIT Professional Education, edX, and OCW. He's a leader in the emerging field of big data, heading the Intel Science and Technology Center for Big Data and leading big data at CSAIL. Madden is the chief scientist at Cambridge Mobile Telematics and a co-founder at Vertica, and has written programs and apps from kids apps to crowdsourced traffic data collection. Professor Madden received his PhD from the University of California, Berkeley in 2003, where he worked on the TinyDB system for data collection from sensor networks. He was also a member of MIT's undergraduate class of '99 in Course 6. In 2005, Madden was named one of the Technology Review's top 35 under 35. So there's a lot more to say, but I won't. Please welcome Professor Sam Madden.
All right, thanks, Lena. Thanks, everybody, for coming. It's really an honor to be here. And I'm going to talk today about sort of big data and what I think big data means. The big data is kind of a funny topic. You guys have probably all heard the word. And my research background really has been in the space of building, I'd say, relational database systems. For those of you who don't know what that means, it basically means the boring old world of systems that store data for businesses, right? Your bank and your, all the websites in the world, a lot of the computer systems we interact with store their data in these relational database systems. But now that big data is such a big thing, of course I have to say I work on big data. So anyway, I'm going to give you my perspective on sort of the big data trend coming from having sort of observed software systems that store and process data over many years. This is something we've been doing for a couple of years at MIT. So the lab that I work in, CSAIL, the Computer Science and Artificial Intelligence Laboratory, Formerly, this is the result of the merger of the Laboratory for Computer Science and the AI Lab in 2004. We set up a program in big data where we brought in a bunch of industrial sponsors to kind of work with us to identify their key problems in big data and kind of learn about some of the solutions and technologies we're building. And we also have this big grant from Intel where we're looking at how sort of next generation hardware is going to maybe take advantage of processing data, and also ways in which we can sort of help Intel to plan out their product roadmap when they think about how hardware and data processing interact. I should say this is work that's been done with many people, especially a group of graduate students who are just fantastic. I'll try and point out their names when possible, but there's too many to list here. And finally, please, if you want to ask questions, I'm totally happy to take questions. I'll sort of try and dynamically scale the talk as we go based on how many questions we get, so don't hesitate to raise your hand if you have something you're curious about. All right? Yep.
Is it Steve or Sam?
It's Sam. I don't know why I got Steve. I guess somebody was staring at their shoes or something when they when they printed my name tag, so that's all right. All right, so let's get on with it. So you guys, I'm sure, have all heard this term big data, right? What it really is about, I think, is this idea that we suddenly have data about everything. It's people sort of woke up one day and said it's not just data in my database that is about what products I have in my product catalog or how many dollars I have in my bank account, but it's I have the ability to measure and collect data about the cars on roads, or these very fine-grained medical events, or all the social interactions that we have through these websites like Facebook or Twitter, or even how people are learning increasingly through these online education initiatives where people are watching videos instead of attending classes, and you get these very fine-grained data points about how long people spend watching every video in the world, right? Or these kinds of sensors that are on industrial equipment that are measuring how well a particular piece of equipment is really performing. So hopefully you guys all know that part about big data. I think you guys probably also, many of you will have heard this definition of big data, which says big data is volume, velocity, and variety, the 3 V's. Sometimes people like to put other V's in this category. Basically this means maybe big data is data that is, lots of bytes. That's sort of what big data sounds like literally is that. But because big data is this sort of catch-all for all data processing problems in the world, we need to throw some other things in there, not just the literal big too many bytes thing. And oftentimes it means data that's coming at you very fast, high velocity data. So this is, you've got thousands of sensor readings a second you have to process. Or maybe data that's just coming from lots of diverse and disparate data sources. Like you have data from Twitter where people are talking about your products online, and you want to somehow combine what people are saying on Twitter with your product catalog and your product ratings and your customer relationship database. And this sort of integrating all this together creates a lot of complexity. So I would sort of add an extra V here, which is what I call non-scalable analysis, or vexing. I know that's kind of dorky, but in particular, I talk to a lot of people, and when you actually talk to them about what their big data problems are, their problems don't have anything to do with having a lot of bytes. People think they have big volumes, but then they'll tell you, oh, we've got like gigabytes of data, and it's like, wow, okay. Their problem actually is that they just don't know what to do with that gigabyte of data, right? They understand that there's some latent value locked up in it, and they are sort of at a loss with how to begin to get that value out. Because maybe their data doesn't naturally fit into one of these relational systems, or they can't easily express a SQL query, or they just don't know SQL, or they don't like SQL, right? So that, I think leads to this set of problems. I'd say either there's some very manually labor-intensive kind of process that people have to go through in order to get some value out of data, or increasingly there are these very complex algorithms, these big machine learning algorithms that people want to run that have to be made to scale up. So I'll give you a couple examples of those. Before that, I just want to say, I actually think that the big data problem, in my mind, doesn't have that much to do with this volume or velocity. And I know some of you in the audience are saying, but wait, I've got petabytes of data and I don't know what to do with it. That's true, but there's not something. We have a set of systems that in the world, software systems, that actually can do a pretty good job of processing very large volumes of data. You could go pay Oracle a lot of money, but they would build a system that could hold very large volumes, petabytes of data, and it probably would do an adequate job of it as long as you were asking a certain constrained set of questions over that data. The thing that you can't do with Oracle is take these very diverse text and speech and audio and sensor data and combine it all together and ask interesting questions about it. And it doesn't really help you to solve these problems at all. So what I like to do is just give a couple of examples, not from my own research. I'm going to give some examples from my own research in a minute, but just some examples that I've sort of come across or that are from MIT. So this is an example from a professor at MIT named Andrew Lo, who probably some of you have heard of. He's a finance professor in the Sloan School, and he is also a member of CSAIL. So what Andrew was interested in was the question of could we build a better model for predicting risk, the probability of financial default, something that does better than the conventional credit score that we all know and probably don't love. And what he did, he got this data, a 1% sample of data from a bank at an interesting time of the world in 2008. Quarter 4 of 2008, so think about what was happening then with finance. And this was about 10 terabytes of data. So this is very fine-grained banking transaction data. And he looked at the distribution. So if you look at this x-axis here, this shows a green dot means a person who's current on their loan. A blue dot means a person who's 30 days late. A yellow dot is 60 days late. And a red dot is 90 or more days late. So if you, for now, just consider the x-axis, you can see that the FICO score doesn't do a very good job of separating the people who are high risk from low risk. In particular, we have this kind of big blob of green, these two big blobs of green people who are, they're kind of spread all through the FICO score. So maybe this isn't surprising. The FICO score probably wasn't really developed to predict whether somebody was going to default on their loan or not. But it shows that FICO score is not a good predictor of this. In contrast, what Andrew did is he spent a lot of time, actually. Just building this model took about 2 weeks of computation time. But he built this model on this data set. And what his model does is plotted on the y-axis. And you can see that if you sort of draw a horizontal line through this, it does a great job of, in fact, separating the high probability defaulters from the people who are not about to default. Can anybody guess what this model learns?
Whether you played before?
So, not exactly. Well, okay, so if I gave you a bunch of financial data, and I asked you to figure out whether I was about to default on my loan, what would you look at? Like if I gave you my bank records, what's that?
Your balance.
Yeah, your balance. Okay, so in particular what the model learns is that if somebody's been getting a direct deposit and it stops, that's a really good indicator that they're about to default on their loan. Which, in retrospect, is probably pretty obvious, but it's kind of cool that the model was able to learn it anyway. So I like this example because, first of all, this is kind of a simple, intuitive thing that it's like, okay, yeah, of course, that's what you would look for, right? It's also, I think, a good example, and it's one of the things we've been doing is working with Andrew a little bit to try to integrate some of the sort of next generation data processing tools to make it so that he can learn these kinds of models more quickly. The computation he had to do with this was quite time consuming and difficult. So this is another example, not from anybody's research at MIT, but I just like it. Does anybody know what kwashiorkor is? Yeah. Yeah, I think it's actually protein deficiency, but it's a form of malnutrition. Okay, it's extremely rare in the United States. It basically, we have malnutrition here in the United States, but it's largely not from people not getting enough protein, right? We have like enough McDonald's or whatever to go around. Okay, so there's this kind of interesting result, which is there's a hospital in Shasta County. In Northern California that reported 16.1% of their patients were reported to have kwashiorkor. So this chart is a little hard to read, but this, the red bar is this hospital, a particular hospital, Prime Healthcare Hospital in Shasta County in Northern California. You can see that, and the red bar is the number of patients with kwashiorkor, and you can see how small these red bars are, everywhere else in California. Okay, you can see that this hospital is clearly an outlier. Does anybody have any idea what's happening with this hospital? So misdiagnosed is close.
Are they testing for that condition?
Well, sort of.
Dyslexic coding error?
Yeah, okay, so it is a form of coding error, but it's not dyslexic. So this is Medicare fraud is actually what this is. Okay, so this is somebody basically, so it turns out, and you guys probably know this, these Medicare, you can up, in Medicare, the reimbursement you get varies depending on the exact type of condition. So just regular malnutrition is worth, whatever, $20 a patient, and kwashiorkor is worth $30 a patient, right? And somebody, some, clever, I don't know who, hospital administrator figured out that they could let's just claim that all our malnutrition people actually have kwashiorkor, and nobody's ever going to figure this out, right? And so some journalists did figure this out. I like this example because the way this journalist figured this out is, well, first of all, think about how many other examples of this kind of thing are sort of latent in the Medicare data, right? And this journalist figured this out because they got some tip from somebody and went and looked specifically at this condition. But wouldn't it be great to have tools that kind of automated this analysis so that we could look at all the kinds of examples of these sorts of automatically find these kinds of outliers in the data that we're looking at. So I'll talk a little bit later about a tool that we've been building that tries to help people automatically understand where outliers in these kinds of visualizations come from. Okay, so all right, so just to give, I'm just going to talk for a couple more minutes about big data in sort of broad brushes, and then I want to spend most of the time here actually talking about some of the things that we're doing at MIT that I think are trying to address some of the challenges around big data. And I'm sort of intentionally trying to just paint a big picture of a bunch of different projects that we've worked on in my research group so that you get a flavor for what it's like to be a professor who works on big data. So, all right, so why is this big data happening now? Well, hopefully the kwashiorkor example illustrates this, and actually the Andrew Lo finance example illustrates it too. There's really, I think, people are increasingly realizing that they want sort of automated pattern discovery over their data. They know there have to be interesting patterns. They don't know how to go after it. And so at some level, this is what machine learning is about. I'm not really a machine learning expert, but we apply machine learning in a lot of the things we do. And there's just, people feel like we need better software tools to make it so that we can access these kinds of machine learning models that exist in the world. The second one, again, is kind of obvious. It's like we actually have the data. We didn't have the data before, right? So we have the ability to collect information from, these smartphones, from the things that we're going to be wearing on our wrists, from, our cars, from our websites, and just at a scale that we simply couldn't before. And then I think the third one is one that is easy to overlook, but the availability of compute and storage is really unprecedented. So just to give you one very simple example of how, to use another buzzword, cloud computing has changed the research that I do at MIT. It used to be the case that there was people in software systems research were kind of they were a little depressed because they would look at Google and they would say, Google's publishing these papers about how they did this thing with 1,000 machines, and how could I ever, as a researcher, get a cluster of 1,000 machines and do any kind of research on that? And suddenly this thing called Amazon AWS happened, and you can go to Amazon, and my graduate students can spin up 100 machines and run them for 4 hours and do some experiment on some piece of software at scale that they simply wouldn't have been able to do, even 5 years ago. And it's affordable. I mean, we can, it's a few $1,000s to run this experiment. It's something that we can sort of manage to do at the scale of MIT, and we don't have to run a dedicated cluster of our own with hundreds of nodes in it. So that's been really transformational for us. And I think it has been for a lot of people. I mean, the amount of sort of usage that AWS sees as a hosting platform is just, through the roof. And this is, if it hasn't already, will be sort of, the biggest part of Amazon's income. So you think of Amazon as a, online retailer, but they've turned this web business into just a tremendous business for them. So the other thing, of course, that's happened is this rise of next generation hardware, like these graphics processing units in machines. And I'll talk a little bit about how we've been using these, specifically GPU devices, for doing data processing. But this is sort of the charter of this grant that we have with Intel. Okay, so maybe I'll pause. Does anybody want to ask a question? This was my big, here's what I think about big data. So that's all I'm going to say about big data broadly defined.
Does the software take advantage of GPUs that are already embedded in existing computers, so you have specialized computers to run that?
No, we're trying to use commodity GPUs. Although, Intel, of course, is also saying, okay, suppose we had this hypothetical device. What would you do with it? They like to ask questions like that to us, but mostly what we've been looking at actually is how to use existing GPUs. And we're interested in the question of what if you took built a cluster of high-end GPUs and assembled them, but still off-the-shelf commodity hardware. We're not talking about building new hardware. Yeah.
I can think of a distinction. I don't think between kind of social data or commercial data versus scientific data. You're trying to discover drugs, and you're trying to figure out how to put up an ad. Maybe I'm getting ahead of the game, but I was wondering, is there any useful distinction? Do you see it as a useful distinction, or is it just all big data?
Of course, I think that there are, as any of you who've worked in the space know, we're faced with this insane proliferation of different systems. Whether it's, we were just talking earlier. There's Hadoop and Spark and HDFS and Hive and Mongo and Vertica and there's literally like 50 different systems like this. Part of the reason there are so many different systems is because these systems are sort of focused on. Many of them have a sweet spot at one particular kind of data, right? And so it may not be, for example, some of them are going to be better at processing. Kind of things like a Twitter feed, like text data that's coming at you at a relatively high rate, but that maybe doesn't have a lot of complicated structure on top of it. There are going to be other ones that are better at, dealing with much more complicated structure, like graphical, not graph as in like, XY graph, but graphical, like as in nodes in a graph, kind of data that might be used to represent, say, complicated drug or protein structures or something like that. And so there are these very specialized systems that are being built, and I think, in fact, one of the challenges of this space is just it's very hard to, say something that is completely meaningful for, every kind of data out there in the world. So.
I'd just like to make one point about the Kwashiorkor situation, and that is that we have to be careful of distinguishing billing data from actual healthcare data, which is completely unstructured and not accessible in any useful form.
I think that's a great, I totally agree that dealing with healthcare data broadly defined as opposed to billing data is a tremendous challenge. So. Yep, sure.
Anyway, do you consider big data more about building something to meet a vision or figuring out what the question is? The context is, I've spent 30 years building software, and I'm watching my daughter become a scientist at MIT, and I'm learning that science is all about figuring out what question to ask to push the boundaries of human knowledge. And it's very different. I build things, and she asks questions, and
that's an interesting question on a lot of fronts. So of course I call myself a computer scientist, and at some level what I do is build stuff, although then we go off and pretend to measure things about it, but really what I do is build stuff too. So at that level I think it's about building stuff. I do think that one of the things that big data is about is helping people to figure out what questions they ought to be asking, which I think is different. It's a change. It's not so much about the traditional scientific method of like I have a hypothesis and I'm going to go test it, right? It's trying to there's this recognition that maybe computers can help with this hypothesis formulation problem, and I think that's is an interesting trend that I see happening. So. Okay.
Generational conflict at MIT.
Well, yeah, I suppose so. I think it is a sort of difference. It's a fundamental difference between, MIT's always there's the scientists and the engineers, right? And they're sort of different. So, all right. So, So I sort of, having talked to a lot of people, and maybe you've seen, I sort of hinted at this already. I think one of the big challenges, the biggest challenge actually we have in this space is trying to kind of understand and organize the data. It's not building these, massively scalable systems, right? Like, MapReduce or Hadoop or HDFS or, whatever it is. It's kind of moving beyond just the scalable platforms and saying, how do I answer some of these questions like, what does my data look like? or how do I understand where this result in my data set came from? Or how do I take this data set and I have some other data set, and how do I combine these two things together, and how do I stick them together in a meaningful way? Or how do I best present data to users so that they can understand it? And these are kind of fluffy questions. They're kind of weird questions for me to ask because I'm used to asking these very okay, how can I make this thing go from processing 100 megabytes a second to 200 megabytes a second, right? But I feel like these are actually the important questions. So I want to talk a little bit about 2 or 3 different research projects we've done in this space recently. I want to start with this slide. This is probably, maybe some of you have seen this comic. This is an XKCD comic where it says pro tip, never look in someone else's document folder, right? But we probably all, sort of have had this problem managing our data at one time or another, right? And relational database systems haven't done anything about this, right? It says, oh my God, I like untitled 40 mom address.jpg, right? And in fact, we had this, so I'm going to talk a little bit about a sort of research umbrella project we've been working on called Data Hub. We started this project by talking with some people at MIT who work with the Broad Institute. They're basically computational geneticists. They collect genome data and build a wide range of tools, and both software tools as well as conducting research to really understand the structure of the human genome and how it codes for proteins and other things like that. So these are 2 postdocs in my research group, and we went and met with these guys. We learned some funny things. So this group manages about 100 terabytes of data, which is kind of a modest-sized database, right? They spend actually quite a bit of money on this, which is a little surprising for an academic research group, but they are paying the Broad to host this data for them. And the data is organized in exactly the way that I showed in that comic, around a collection of shared folders. Basically, they have a big shared file server they all stick their data into. Okay, and they, when you ask them, do you like this? Some of them think this is exactly the right way they ought to be managing the data. But when I look at it, you hear some kind of weird things. So you ask them, how do you work on data sets? Some new graduate student comes in the group, and their answer is, well, the guy makes a copy of the data, right? But doesn't that mean there's a lot of duplication? Yeah, sure. But that's why we have 100 terabytes, right? Okay. So there's a lot of redundancy here, right? So you ask them, well, what if multiple users want to collaborate and work on the same data set? And say, well, yeah, sure, I guess that's okay. It's in the file system, they can do that. But we don't really know anything about, concurrent modifications. You better not do that, right? If you want to modify the data, you better make a new copy of it. We don't really actually even understand who's using a particular data set, because they're just files in a file system. And so collaboration is hard. They can, you ask them, well, don't you need to delete data sets sometimes? And they say, yeah, sure. And they say, well, what if this data set you're deleting is really important? And they say, well, I guess, we hope it's not. We hope that we have this institutional memory that'll tell us which data sets we really cared about. And I find this, this is a little bit concerning, because it's these people are trying to conduct scientific research, right? And you don't necessarily like the idea that the underlying data might disappear underneath you. Okay, so there's sort of not a good, they don't have a good way of managing all these different data sets, the dependencies between the data sets, who's using them, or really how to sort of track or organize them in an institutional kind of a way. And you talk to other people in other organizations, it's not like this is unique to some weird research group at MIT. I think this is actually pretty consistent in big companies, that they have lots of people with lots of different places that the data lives in, and they're not doing a very good job of keeping track of all of it. So we've been building the system we call Data Hub. This little logo is an amalgam of an elephant and the GitHub logo. So if you're wondering where it comes from, elephants are somehow the universal symbol of databases and Republicans. I don't know why, but they are. I guess they never forget. Anyway, so elephant plus GitHub, for those of you who know what GitHub is. So the idea with Data Hub is it's a collaborative version management system. And so for data sets. So for those of you who don't know what version management is, it's sort of a popular idea that's used for source code control. So when developers are collaborating, there are these really great tools that allow them to sort of collaboratively work on source code. So two developers can concurrently modify the same file, and when they make modifications, there are these tools that help them to figure out, sort of resolve concurrent edits to files. And it also tracks the history of files over time, and you can have these, very nice, you can create what's called a branch where one sort of developer can go off and develop some feature independently of the other developers without messing up what those other developers are doing, because he's changing the state of the source code underneath them. So what we want to do is the same sort of idea for data sets, right? We want to have this notion that there are these data sets that an organization has that are being maintained and evolving over time. We want to track the relationships with them and the differences between them, both for minimizing wasted storage as well as for making it so that users can understand the connection between the data that they're using to answer questions. They can say, where did this result in this database come from? And they can see that it came from these three underlying data sets that they got from some place on the web or something like that, right? And then you want, of course, good search features on top of it. The other thing that you want to build, and this is actually what I want to talk more about, because I think the versioning stuff is, although it's a great research topic and we have a bunch of research papers were planned on it, it's might be a little bit dry for this audience. So the other thing that we're talking about are what I call sort of data access features. So these are features that make it easier for users to get this kind of latent value out of their data. And I'll talk just quickly about a few of them, so I won't go through this list right now. So we've built a very simple prototype of Data Hub that has an interface that lets users sort of upload and keep track of all their files inside of their data sets inside of their organization. We have this notion of data as sort of moving from text files into more structured tables and sort of evolving as we do that. And we have built some tools that make it really easy to get data out of your text files into into structured tables. You can upload data, you can share data with other users, so on and so forth. It's the interface itself is relatively sort of simple, but I'll show you one example of this text file insertion thing, which I think text file loading thing, which I think maybe will illustrate one of the problems that is pretty cool that we can solve. So this thing here is a log file from a system called Hadoop. So Hadoop is a storage system that a lot of people in the big data space use. If any of you have ever looked at a log file, they often look like this. They're just these kinds of like big, long, almost tabular sort of lists of information. So it says, this says somebody, some module called data node received some block from some machine on the internet at some particular time. Okay, and these records are kind of similar in structure, but they have somewhat different structures. There's different things that appear in these log files. So what we wanted to do was to have a way to go from this into something you could put into your relational database and ask questions over. So our idea is to let people do sort of example-driven telling us what the mapping from a log file is to a table, and then build a tool that will automate this process for the entire log. Okay, so what the user does is they specify these two inputs, okay, and then they specify that this record here actually should look like this tabular thing here, and this record here should look like this tabular thing here. So the output format should be a timestamp and a source IP address and a destination IP address. And then there's some records that don't have IP addresses, so we won't have those. So now what we can do is we can run this refine tool, and when you refine it, what you see is it learned from those two examples I got a way to transform the entire data set into tables like this. So it's this example-driven sort of data cleaning or data refining, if you like. And then, of course, once you've done that, in Data Hub, you can import this whole thing into a table, which you can then run queries on. Okay? So that's one example of a kind of, I think, cool tool that we're building in this space. And then there's a whole bunch of version management features, which, as I said, I won't go into too much detail, but every data set has a history of versions attached to it, and you can ask questions about who made which changes at what time. All right? So I'm going to talk about some more examples of some kind of research problems we're working on in this space. But one of the things we're trying to do is to use this in a kind of real way at MIT. So I feel like we need to sort of have a dog food eating exercise, if you will. That is, use our tools for doing cool things on campus. So I thought you guys are an MIT audience. Maybe you'd like to hear a little bit about some of the things we're doing. So the idea is to sort of have this data hub host a whole bunch of information about campus. So when you start thinking about all the data that's available on campus, probably at the, you guys have this problem at all the companies you work for. There's a lot of data, but it's in these locked up in these kinds of silos, right? So just think about what MIT knows about the people on campus, right? ID card swipes, all the network packets that we send, expense reports, medical data, payroll, parking garages, what buses I ride, what course catalog entries I appear in, what the registrar has a database about that contains information about me, my HR benefits, events that I participate in campus, seminars on campus, the energy utilization of my office. I mean, there's a ton of these different pieces of information that actually MIT mostly is recording, but recording in some independent database. There's no place you can go. They have something they call the data warehouse, but it's not pretty, and it doesn't make it easy to get at this data. And then furthermore, people have lots of other information that they might want to combine with this. So their own personal data, for example, like location information about where they were, as well as public data sets like transportation data about what's happening around the university. So we've been trying to kind of use this data hub as a source to host a lot of this data, and we've really just done some very simple things. We have a project to collect information about how many people are connected to Wi-Fi, every Wi-Fi access point on campus, and we're making that available as a data set to campus so that people can play with it. And this is kind of cool because it lets you build maps about where activity is on campus at any one point in time, because of course these things and our laptops are connected to the Wi-Fi networks all the time and leaving a little digital signature of us. Okay, so what are some of the kinds of cool things you could do with this? Well, I don't know. Just consider this first one. Like, how would you answer the question of, is going to class correlated with getting better grades, right? And you'd need to take information from 3 or 4 different places, like understand, well, how many people actually are going to class over time, and what grades did they get, right? And there's a bunch of kind of cool or challenging questions around this. First of all, you need to figure out how you combine these data sets together. You also need to kind of socialize the idea with people like the registrar. And grades there are real rules governing what the registrar actually can do with grades, but people are very protective of these data sets. The notion that somebody has spent time curating and owning this data set and trying to socialize the idea that some of this data should be shared more broadly with a community is something that you really have to have a conversation with, and you have to think through a lot of these privacy and kind of security questions that this might bring up. And so that's been kind of a fun conversation to have with a variety of people on campus. But I think I'm pretty excited about doing this. We have a team of programmers who are now just starting to work on this. So, all right, so with that, what I want to do is spend kind of the last 20 minutes or so talking about a couple of the other research projects. Mostly I'm going to show 2 demos. I'll have one sort of technical thing, and then I'll show a couple of demos of some cool software systems we built. Does anybody want to ask any questions? Yeah?
So far you used the word curating only once, 40 minutes.
Okay.
Junk data is junk data. How does one know the distinction between something that has been curated and something that hasn't been?
So I think data curation is obviously, I am totally with you, that data curation is a huge challenge, and it's even more of a challenge in this world of, the data is no longer being sort of manually entered by people and then double checked, right? The data is coming in from God knows where, right? So I think one of the challenges we have to work towards is building tools that try to automate this curation process how we can, in ways that we can. You're absolutely right that a huge danger in this space is making inferences based on data that is, as you say, junk. And so I don't have I don't have something right now to tell you about this. I'm happy to talk about various research efforts that people have are engaged in our research group and elsewhere to try to understand the veracity of data. There have been some really cool research projects where people have looked at trying to understand copying relationships between data, which you can understand why that might be really important, because if you have 3 data sets that all tell you some fact, maybe that increases your confidence in that fact, but boy, you shouldn't increase your confidence in that fact if all 3 of those data sets are being copied from the same underlying data set. So I think understanding this sort of the connections between data is a really important thing, and it's going to help us to get towards this. That's part of what we're trying to do with this data hub platform, but I certainly wouldn't claim we have this figured out, and I agree it's a huge challenge. Yeah?
I find it interesting when you're talking about like opening up all this data from MIT to the community to look at. I don't the most part, I don't see a lot of data being made available in large data sets, except for very select institutions. So do you think that this is an opportunity for MIT to lead in showing other organizations how to open up their data for the public good?
That sort of is, that's a part of a goal of what we're trying to do, and we're trying to sort of demonstrate a really positive way of doing this. Like, I don't know if any of you have ever gone to this data.gov website. So data.gov is like, it's a very well-intentioned effort, but when you actually try to, so data.gov is an effort by the federal government to release data sets about lots of different aspects of the government. When you actually get one level below the front page of data.gov, you end up at, every organization has their own, proprietary way of describing their data, down to the, one of them is using CSV files, and one of them is using Excel, and one of them is using some weirdo proprietary format that you can't even open, and they don't use the same schemas to describe their data, and it's a mess, right? And so trying to think about how you do this in a way that encourages people to publish data in a more useful format, I think is certainly is a goal of ours. We're at the early stages of this, but I think if this is successful, that would be our goal. So, yeah.
This data hub idea, is it sort of in the open domain? Available for others to play with?
Yeah, and so the prototype system we built is available. It's open source as a BSD license. You can, or an MIT license, I guess. You can download it and play with it. I should say, I'll give you the caveat. I mean, most of the things I'm going to discuss today, let me just think about this. I think all of them are available to play with in some form, but it's all research quality code. So, we build prototypes of things. The graduate students have built them. Their graduate students are great, but their focus is not necessarily on building, enterprise class software. So it's the sort of thing that's meant to show, demonstrate what can be done, not necessarily, some of these things are being productized. There are startup companies that are working on them, but they're not quite at the level of, here's a product that I would encourage you to put your mission critical data in. Okay, I'm going to move on, and then we'll take some time for questions at the end. So, all right, so just a couple of research problems. We're working on a lot of different things in this space. I'm going to talk about 3 of them quickly. So the first one I want to talk about is a system called BlinkDB, which is about basically how to use statistical sampling to answer queries quickly on data. And this really is the most sort of big data-y of the big data in the volume sense of data of these projects. The other 2 are a system for sort of interactive data presentation using GPUs called MapD. And then the third one is a tool for sort of understanding where outliers come from in data sets called Scorpion. Okay, so let me start by talking about BlinkDB. Okay, so BlinkDB is an approximate, to throw out a ton of buzzwords that may or may not mean anything to you, an approximate database query processing system on Hive and Hadoop. So this is work that I did with some folks at UC Berkeley who are actually now off I think all of these people are now at Databricks, which is the company that's commercializing Spark, if any of you know about Spark, as well as my postdoc Barzan. And so the idea here is actually quite simple. It's this observation that there are many applications that are going to be sort of tolerant of quick approximate answers on data. And I'm sorry about this logo, which is like, it's really annoying. So the trade-off here is that we're going to tolerate a few % error in answers. We're going to answer questions by looking at samples of data, very much like statisticians look at samples of data in order to compute the polling results or other things. You don't have to ask everybody in America to get a good estimate of who's going to win the next presidential election. So we're going to trade off a few % error for much, much more efficiency. Just like in a poll, we're not going to have to look at every data element in the database. We look at a random sample of them, and then we estimate the answer to our queries from those random samples. To give you an example of what this is, imagine why you might want this. Imagine you're running some operational system and you suddenly notice that some subset of the users are experiencing some outage, right? What you want to do is to understand very quickly, look at the set of users experiencing the outage and compute some information about them. Like, is it the fact that they're coming from a particular ISP or running on some particular platform? And it may be important to do this with really, really low latency. And you may simply not have time or want to spend minutes or hours to look at every piece of data in your database to answer this question. Okay, so users are kind of overwhelmed by volumes, and they increasingly want interactive response times. So the model, so for those of you who haven't seen SQL here before, this is a very simple SQL query that sort of embodies this response time thing. Maybe what we want to do is to find the average response time from our data set, where we partition the data up by region of the world. Okay, so we say select average response time from data group by region. And then what we do in this BlinkDB system is basically add this one extra expression which says I'm tolerant of a 1%, I want a 1%, I'm tolerant of a 1% error with a 95% confidence interval. So I want my error, my end result to be within plus or minus 1% of the true answer, 95% of the time. Okay, and what we're doing in BlinkDB is pretty straightforward, actually. We pre-compute a set of samples of our data, many of these samples, and we store them. And the idea is these samples are small, so we can store lots of them. And then at runtime, when we're answering a query, we pick a sample to use to answer the query, and then we compute bounded error over it. And what we really have done, the research has done, is to take this is a very simple SQL query where it's easy to estimate these confidence bounds, but more complex SQL queries that have nesting or complicated filter clauses, where clauses on them are much harder to sort of make this work for. So we developed the statistical estimation tools to allow us to answer these kinds of questions over these SQL queries. Okay. If that sort of makes sense at a very high level. I think I don't have time to go into too much about the details. This is just sort of shows the architecture of how it works. We compute these samples offline. We take these queries that come in, we compile them into it, we built this on top of this Hive system, which is a pre-existing database. But what we built is this sample selection module, which when a query comes in, decides which of these many pre-computed samples to use. And then we pick the sort of set of samples that we hope will meet our latency guarantees. Then we run these queries on Hive. We use the results that we get out. We estimate these confidence intervals on them. And then if the confidence intervals don't hold, then we may have to go recompute the answers to our queries. All right?
Good question.
Yep.
So your samples are your clue sets, right?
Our clue sets.
Clues. In other words,
Yes,
you're predicting,
yes.
you know what the outcome's going to be. You've got your samples of what your outcomes are going to be. So
Yep.
each time you run your large piece of data through it, and
So
you have the matches, you're going to have the result.
Yeah, that's basically right. So we have some data set, right? Like imagine it's this data set of all our observations of latency in the last few days in our system, right? We have these samples that we're sort of maintaining over time. So as new data comes in, we update these samples a little bit. These samples are of different sizes, and we need different size samples based on in order to sort of meet latency goals. Like if you want an answer within 1 second, we can use a smaller sample. Or if you have a broader confidence, more tolerant to error, we can use a smaller sample and give you things more quickly. So I think yes. The answer to your question is yes, but I can.
That I've done, you have your clue sets, you have your samples, you feed your corpus of data into what you think the results are going to be, and then once you train the engine.
Yeah, I think it's a little bit different here because we're sort of, these samples are being they're just a direct, there's not a model that's being used to, on the data itself. The data is just, these are just subsets of the data. And we're just picking a subset of the data to run this query on, and we then built this module that sort of estimates how good our answer is over this thing. Okay, but just to give you a sense of how well this works, so we took a 17 terabyte data set from a media analytics company that basically had these video logs of the different accesses of videos online, basically, from a bunch of different users. And this data was running partitioned across 100 nodes. It was about 17 terabytes. And we just measured the performance difference of our system, BlinkDB, versus this unmodified Hive system, which is an existing SQL-based database. So this is on a 2.5 terabyte subset of the data, and this is on the 7.5 terabyte table in this data set. And what you see is that well, there's a couple of observations. First of all, notice that this is an exponential scale axis. Okay, so our system is taking about 10 seconds, 9 seconds here to process this. Hive takes 2,000 seconds to answer this query. Okay, you scale up to 3 times as much data, and Hive takes 3 times longer, and we don't take very much longer at all, right? Because actually, the query processing time is sort of independent of, it is really dependent on the number of samples that you need to answer the query, not the size of the underlying data set. So that's one of the cool things about this technique. it's so much faster. It's like you might say, why is it so much faster? Well, it's so much faster because you don't, sampling is an incredibly powerful technique. You don't really have to look at very much data in order to get pretty good confidence intervals over things. So it really is just the fact that, in this case, we're looking at, 1/200th of the data, right? And so we're 200 times faster. That's all there is to it. It's just that, you can use this statistical sampling in order to make this kind of work out.
So are the answers the same?
Well, I can point you. This is obviously a sort of a cartoon of a graph. I can point you at the paper where we looked at. The question you have to answer is. You have to ask is, did you satisfy the confidence interval? Were your confidence intervals and error bounds correct? And so in order to answer that question, you have to run a lot of queries and measure the fraction of the time that you miss. And our system doesn't miss, which basically tells us that the sampling theory is correct. But that is, sometimes your answer is not, if you have a 95% confidence interval, what that means is that 95 times out of 100, with a 1% error bound, 95 times out of 100, your true answer will be within 1% of the answer that you emit. And those other 5 times, who knows what you get, right? Yes, the system meets that guarantee. And this is a standard sort of statistical notion, this confidence interval thing. Yep.
So if the underlying data set is getting new contributions at a high rate or changing at a high rate, those pre-computations kind of picking up with that?
This is a great question, and one of the a natural question you might ask is, why do we do this pre-computation approach at all, right? Couldn't you have randomly pick a new set of records every time? The answer to that is that because of when these systems are stored on disks, randomly offsetting to a bunch of places in disk is really, really slow. So we want these pre-computed samples. Similarly, if data is randomly coming in and data is being inserted all the time, doing lots of little updates to data that lives on disk is painful. So what you need is some way to sort of batch the updates into these buffers that are on disk. So we have this sort of buffering and then batch writing out to these samples. Yep, one more question?
Yeah. On the sampling side, actually, depending on how, this is more, my question is more related to the sampling theory itself. Depending on how heterogeneous the data is, different sampling methods may or may not work. Have you considered this in the type of sampling you're doing for the type of data you are trying to analyze? For example, if there are outliers, we might easily miss them.
Okay, great. So there's some questions that I think there's some questions that you simply cannot answer correctly with this approach. So if I ask you for the largest value in your data set, right, sampling is never going to produce that, right, or do a first approximation will never do it. So we don't let you ask that question. You can ask instead, what's the 95th, what's the 95th percentile or something, right, which sampling can answer effectively. But yes, this is a good point, and there's lots of ways in which, lots of little details to get the sampling theory to kind of work out. One of the things that's especially problematic are queries that ask about rare subsets of the data. So if I say, for example, tell me the average salary of employees in Cambridge, Massachusetts, maybe only 1% of the data is in Cambridge, Massachusetts, right? So then if I ask about Cambridge, Massachusetts, or maybe 1/1000th of the data is in Cambridge, Massachusetts, if I ask about that 1/1000th of the data and I have a 1% sample of the entire U.S. population or something, that super small amount of data that actually corresponds to Cambridge, Massachusetts, and so it's very hard for me to give good confidence intervals around that. So one of the things we've worked on is maintaining samples that are sort of stratified on particular attributes that you're going to need to query on, if that makes sense. So we've thought about it some. We're certainly not we're not experts at this stuff. We sort of go and read the stats books and remember what we learned in our graduate stats class and try and apply it. So. Okay, so I want to talk now about, and this is where we're going to switch to the sort of the end of the talk. Like, I know you guys' eyes are glazing over. I'll do a couple demos, really. Just want to show you some other cool things we've built, and I'll give a really quick caricature of why they're, how they work. So this is a system that was built by a guy who worked with me named Todd Mostak. The system's called MapD, and it uses GPUs. So for those of you who don't know, modern all essentially modern computers have this chip in it called a graphics processing unit. And the graphics processing unit is interesting because although it was conventionally developed for like rendering 3D pictures on your computer, they have more recently shifted towards being a more general purpose computing platform that can be used to in parallel, apply some operation to many, many data elements. And so what we're doing here is actually using this GPU to very efficiently scan large data sets. So and the demo I'm going to show you is a demo with some Twitter data. So this is I'm going to shift over here. Sorry about that. It'll come back, I hope. So each of these little dots that you see on this map is a tweet. So this database has about, we have a version of this that has about 1 billion tweets in it. Right now we're only looking at about 50 million of them. These are over a 1-week period in, I think, last December of 2013. So this is a slightly old data set that I've loaded into this. But you can click on one of these tweets. And you get something weird, right? Like, what do people say on Twitter? They say, nothing annoys me more than Dan Humphrey pretending to be poor on Gossip Girl. Okay, like, whatever. I don't know what this means. This is not a show I know anything about. People write really inane things on Twitter, right? But the interesting thing is that you can get kind of actually quite a lot of kind of insight out of this data set as an aggregate data set. And that's what we're trying to do with this particular tool. So we're analyzing the content of all of the tweets. And the way that we're doing this, actually every query, every screen that you see here is being rendered by exhaustively scanning. That is literally looking at every one of these, in this case, 50 million tweets that's stored in this database. And we're doing that because we have this GPU that can do this really, really fast. So every one of these animations can be rendered in just a few milliseconds by exhaustively scanning all of the data. So what I'm going to do is just show a couple of examples. So first of all, this shows like a word cloud of the most common words. Again, the most common words in the data set as a whole are these very saccharine, kind of like platitudes or whatever. Love, day, good, happy. People write some really like, when you look at the whole. But let's look at a particular thing. So let's look at all the words that contain, all the tweets that contain the word rain. So those are all the tweets that contain the word rain. And maybe rather than just looking at all the tweets that contain the word rain, because New York City always has the most tweets that contain any word, I want to kind of divide the background the frequency of the word by the background frequency of tweets in that region. So now I get sort of the density, the fraction of the tweets that contain the word rain. And then I can actually animate this, and you see this kind of pattern that comes out, right? Which is this rainstorm moving across the country because, well, people tweet about rain when it's raining, right? So you get this kind of aggregate pattern that comes out of data. And again, every frame of that animation was being generated by exhaustively scanning the entire data set, nothing pre-computed. You can see other interesting things like snow, the northern part of the country, there's a sort of a line where it just basically doesn't snow, so people don't talk about snow. You can see, here's a good one for the Northeast. That's the word Duncan. Okay, so it's like a very regional kind of a thing, right? Just to show you one other example, that's y'all. Okay, so people don't use y'all again, above some kind of dividing line, basically, in their tweets. So this is a pretty cool tool actually for getting a lot of very quick insight out of Twitter data. And again, it exploits the power of this processing thing, but I think it illustrates we have this new capability, which is interactive visualization over a massive scale data set that simply didn't exist before. And I think what's valuable about this is the interactive visualization, I think, more than the new platform that we built. But we kind of have enabled this with this platform we built. Okay, so I have about, I think, 5 minutes left. I'll try and wrap up by 8 o'clock. You guys asked a lot of questions already, so. All right, so I want to just quickly talk about this, the notion of understanding why results are the way they are. So this is a tool we call visual provenance. Provenance is like the origin of things. Where did something come from? And we sort of started thinking about this when we started looking at some of these visualizations. I think like the Kwashiorkor example is a good one. Like, why is that one hospital so far of an outlier away from, so much of an outlier relative to the other bars? You see that very visually, right? And this is true of a lot of outliers. Here's, this is, if you search for Central Park on that tweet map thing, you see Central Park kind of light up, and yet for some reason, there's some part of New Jersey where a lot of people are tweeting about Central Park, right? All right, so it'd be nice to have a tool that lets you ask these questions to sort of identify why outliers exist. So this is work of my student Eugene Wu. He made me promise I'd show a giant picture of him whenever I give this talk, so there he is. So let me sort of try and tell you what I mean by why. And this is, we started thinking about, well, how would you explain an outlier in a data set? And what we thought was, we kind of realized that what you want to do is, so in a visualization like this, imagine I've got a graph of some distribution by country, right? Each of these bars is actually computed by computing some statistic over the bars that correspond to that country. So these brown bars, this brown bar comes from these 3 brown records from Italy, and so on and so forth. So if we say the U.S. here is an outlier, right? The U.S. is an outlier group here. Maybe what we want to do is to find the set of records that if we were to remove them from the input data set would make the U.S. not be an outlier anymore. So that's what we mean by sort of explaining the outlier. And then what we want to do is to come up with a predicate that actually describes what it is about those records that we removed that made them an outlier. Okay? So we want to find those common properties. So maybe it's, this is Warren Buffett and Larry Ellison, and like they're the, these are people who have job title CEO, and we removed them from the data set because they're really rich and everything looks normal or something, right? So what I want to do now is, this turns out to be sort of an interesting problem. It's actually quite a hard problem to solve computationally because it involves a sort of exhaustive search over all of these possible input records to find all possible predicates and then evaluate the one that works best. And so we developed some heuristic search methods to solve this problem. But rather than tell you how we solved it, what I want to do is just show you a demo again of our tool. So what we're looking at here is a data set. This is some sensor data from temperature sensors inside of a building. And the top is the temperature distribution. Each dot here represents 1 hour. The data is sampled at something like every 30 seconds from about 50 sensors. So each of these dots is an aggregate of several thousand data points. Okay. The top is the average, and then the bottom is the standard deviation. Okay, so you see at this point here, the standard deviation kind of goes crazy. Something weird starts happening with these sensors. And you can see actually this is a distribution of all the individual attributes over here. So this is the temperature attribute. I can brush over one of these, and I can see that hopefully this will work. If I remove the temperature data, that didn't quite show what I wanted. If I remove the data from very high temperature sensors, well, things go back to normal. Okay, so the problem is that there are some sensors that are producing very high temperatures, but I don't really know what is going on, why those particular sensors are doing this. So what this tool lets you do actually is highlight some data points that are too high. I can click on those and say those are examples of data sets that are too high. I can click on some other data points and say these are examples of data points that look about right. And then you run the tool. I've already run this because it takes about 30 seconds to run, so I just want to show you quickly what it does. But what it produces when I do this is this predicate here that says sensor ID is equal to 18. And you can see if I mouse over sensor ID equals to 18, these gray points represent the old distribution, the orange points represent the new distribution. So what it actually explained to us was that the problem was that sensor ID 18 was producing these really high variance things. Okay, and it turns out when you dive into this a little bit deeper, this tool doesn't tell you everything, doesn't tell you the whole story, but it helps you to identify the story. I can now zoom into sensor ID 18, and what I discover is that sensor ID 18, these devices were this very old wireless sensing technology. The devices didn't have voltage regulators, and it turns out that the battery voltage drops, decays over time on these alkaline batteries, and the microprocessor continues to run, but the temperature chip, the chip that's sensing the temperature, goes haywire when the voltage drops below some level. So you get these crazy sensor readings after the thing has been running for a few days because the voltage drops below some threshold. Okay, so that gives you an example of kind of a cool tool for helping us to understand where these sorts of outliers kind of come from. And we think this could be really useful in cases like this, quasi-OR thing. Like, okay, I want to look at this data set and understand what are the things, I computed this from this underlying data set, but I need to go back to the underlying data and ask questions about it. And this is kind of a capability that people haven't really previously had. Most visualization systems, you put a chart in Excel and you get this static thing that you can't interact with, you can't brush over, you can't ask questions about. So we feel like being able to ask questions over visualizations is actually a really powerful thing. Okay, so I'm going to skip over the why is this hard. I'll come back. Let me just wrap up, and I'll take a couple questions. So I think of big data, so just to wrap up, I think of big data sort of as a cry for help. There's a lot of people out there who are just desperately trying to understand how they can use their data to achieve what they want. There's lots of good research on building scalable systems, but I don't think this actually tells people how to go solve the problems they need to solve. So this Data Hub platform we're building is a sort of general purpose platform that encompasses a bunch of different research tools, like what I showed you, to make it easy to find, visualize, query data securely and efficiently. And there's a bunch of interesting research problems here that we've been publishing papers on, like this scalable visualization, data approximation, and these kinds of data analysis tools. So thanks everybody for coming. I hope you enjoyed it. I have time. I'm happy to take questions. It's just about 8 o'clock. So thanks again. Yeah.
So how well is Scorpion able to deal with like very high dimensional data sets? Like how high dimensional can you get before everything starts to fall apart?
So the performance is it's a good question. Obviously, the performance scales with the number of attributes that you feed into it. It scales exponentially with the number of attributes that you feed into it. So the kinds of data sets we've evaluated on are sort of the 10 to 20 dimension kinds of things. We have these heuristic search algorithms that do a pretty good job. Like this data set I just showed you is several million data points and something like 10 or 15 attributes. Beyond that, it's going to have trouble. It does, of course, the tool lets you specify a subset of attributes you want to run on, but that may or may not satisfy you. So if you want really, really, really high dimensional data, I think, that's a classically hard problem. So is there another question?
Quick question. So if we want to play with the visualization of one of your Scorpion piece, where do we go look for?
So the Scorpion, if you search for MapD, you can actually access that Twitter demo that I was just showing you. You're welcome to play with it. Scorpion, we don't have the demo publicly accessible, but the source code is there. If you search for Scorpion, Scorpion MIT database group or something, you'll get a link to the source code and you can download it and play with it. So, yep.
What if we weren't ready for Scorpion, but we just sort of said, well, I'm thinking about collecting data and what kind of questions can I ask, and just sort of more 101 questions?
So, I guess trying to think about, I'm interested in the question of building tools that try to sort of automatically state questions over data, but I don't yet have something that I can show you exactly for this. The traditional name, this is why data scientist is the most, sought after position in the world, right? Because there's a lot of people like you who I say, I have this data, I know there's something good, what can I do with it? And they think data scientists will help them solve this problem, so. Yeah.
So you've seen a lot of different kinds of problems and applied your techniques to a lot of different kinds of problems. Could you pick one particular problem you've seen or that you've either worked on directly or just sort of seen out in the public sphere where you see massive opportunities for improvement by a little bit of application of big data techniques?
That's an interesting one. So I think I think a lot of the problems I'm talking about are sort of motivated by relatively novice users. So I think journalism, for example, is an example where I think journalists could do some really awesome, incredible things. And you see some of these guys, like the people at the New York Times, who have a great data science team. Nate Silver is a good example, or I'm blanking on his name. The New York Times has a visualization team that's just outstanding, really smart people. But this isn't something that, not everybody has the resources of the New York Times. And actually, even the reporters at the New York Times don't have access to these guys every time they want to run something. So if they had tools that could help them, I feel like, discover things. They often have interesting data sets, but they don't really know how to go about getting the value out of that data. So I feel like that's one area where you could make a really big difference. If you ask where is big data going to have the most impact in the next 5 years from a societal point of view, I think the obvious one that a lot of people are predicting is medicine, just because we don't know how to get and we know there's interesting things to be learned from all this medical data that we're collecting. And if big data can deliver on its promise, it ought to be able to really help us to do something about crazy healthcare costs and some of the diseases that we have a hard time treating. But we'll see if we can get there.
One last question.
Yep.
I actually just started as a data scientist, and it's a new thing for me as a physician. And one of the things that I'm having trouble figuring out is how to prioritize tasks. Because you have this data set, and you don't really know exactly what questions to ask until you can test, but then there's a business outcome that's wanted. So how do you think about prioritizing the different types of analysis to do on the data and kind of saving time and getting answers?
Yeah, I mean, this is it's a very interesting question, and wouldn't it be nice if you had a software tool that could do this for you, right? I think the classical statistical answer to this, right, is you would look for the attributes that have the most variation or that are most correlated with some output that you want. You would try to do things like prune out attributes that don't seem to have a lot of discriminatory power or don't have a lot of interesting variability. You sort of look at one dimension at a time and find things that are correlated. Use dimensionality reduction techniques to find groups of attributes that maybe can be combined together. This is it is, I think, inherently sort of an exploratory process, and it's one that that's your job, right? That's why it's work. Anyway, thanks very much, you guys. I'll stick around and take more questions.